Welcome back to Corporate Finance. Today we're going to turn to a new topic, interest rates, but before doing so, I want to briefly review our last topic, the time value of money. As you'll recall, we started off with some intuition, then we introduced the tools associated with the time value of money, namely the discount factor and the timeline. Then we applied those tools to move money back in time via discounting and forward in time via compounding. We discussed some useful shortcuts to compute the present value and the future value of cash flow streams that we commonly come across in practice, streams like an annuity and a perpetuity. And then we closed out the topic by talking about taxes and inflation and their impact on our dollar returns and our ability to consume goods and services. In this topic, interest rates, I want to start off by talking about interest rate quoting conventions, and I want to talk about how to compute the present value and future value of streams of cash flows when they arrive at irregular times, non-annual, and when the compounding is non-annual as well. So let's get started. Hi everyone, welcome back to Corporate Finance. Today we're going to be turning to a new topic, interest rates. But before doing so, I want to briefly review our first topic, time value of money. So we started off that topic by introducing the concept with some intuition. And what we did is we showed that cash or money received or paid at different points in time has a different time unit and as such can't be added, much like different currencies can't be added. Then we introduced the tools associated with the time value of money, namely a timeline, which is just a visual representation of when money is coming or going, and a discount factor, which is our exchange rate for time. It's what we used to move cash flows forward and backward in time. Then we use those tools to discount cash flows, that is, move them back in time, and compound cash flows, or move them forward in time. We introduced some useful shortcuts, namely the present value of an annuity formula and the present value of a perpetuity formula, as well as formulas for the present value of a growing annuity and a growing perpetuity. Then we closed off the topic with a discussion of taxes and inflation and investigated how those two concepts would impact both our dollar return and the purchasing power of those dollars. Now I want to turn to interest rates in this lecture, and this isn't so much a new topic as much as it is really an extension of the time value of money to incorporate institutional details and make things a little bit more realistic. So we're going to talk about interest rate quotes, and we're going to learn how to deal with cash flows that don't arrive once a year, but maybe arrive monthly or semi-annually. And we're also going to discuss how to deal with compounding of interest when it's not just annual. So let's get started. So here's a snapshot from December of 2014 of rates on 5-year jumbo CDs, where CD just stands for Certificate of Deposit. It's a savings vehicle that most banks offer, and here's 1, 2, 3, 4 banks. All right. Now, the jumbo, that just refers to, I think, a minimum deposit of $100,000. So these are big deposits. And one of the things you notice when looking at these rates, when you're looking at these savings vehicles, is that each one has two different rates. It has a rate and an APY, and these numbers, 2.37, 2.4, they're different. So that begs the question is, why are they different? How are they related? And most importantly, which one is going to tell me how much money I'm going to make when I invest in this product? Well, let's go through this, starting with the rate. The rate refers to the APR, the annual percentage rate. That measures the amount of simple interest earned in a year. Simple interest is just the interest earned without compounding, ignoring compounding. And if you're wondering what compounding is, we're going to talk about it. But just as a preview, notice underneath rate, we have compounded daily. Okay. Simple interest ignores that compounding frequency. Okay. Now, many banks quote interest rates in terms of an APR. The problem is the APR is typically not what we're going to earn or what we're going to pay. For that, we have to turn to the APY, or the annual percentage yield, which is really just another way of saying EAR, or effective annual rate. See, the EAR, that measures the actual amount of interest earned or paid in a year. That's what we care about, the EAR. That's the number we care about. The rate, or the rate or the APR, that's just a quoting convention. Now, how are these different rates related? Well, before showing you the explicit mathematics, which frankly are almost trivial, let me emphasize the following. The EAR is a discount rate. The EAR is what matters for computing interest and discounting cash flows. The APR is not a discount rate. It's a means to an end. It's a quoting conventions. We're going to use APRs in conjunction with compounding frequency information to get at an EAR or at a periodic discount rate, which I'll introduce in just a moment. So remember, EAR equals discount rate. APR equals quote. Now, how do we get from one to the other? How do we move from APR to EAR or vice versa? Well, here's that simple mathematical formula I referred to just a moment ago. The EAR is related to the APR by this equality. Okay. Well, what's going on here? K, that's just the number of compounding periods per year. So imagine we had monthly compounding. That would imply a K of 12. How about semi-annual? That would imply a K of 2. And I'm going to introduce a little bit of notation here. I is the periodic interest rate or the periodic discount rate, and that equals APR over K. Let's do an example. So imagine we're investing $100 in a CD offering 5% APR with semi-annual compounding. How much money will we have in 1 year? Okay. Well, there's actually two ways to approach this problem, and we're going to do each in turn. The first thing we always do, is we draw a timeline. And so today, period 0, we're going to invest $100. And the question's asking how much money are we going to have in 1 year? Now I've left this as a question mark to emphasize the fact that there are two ways to go about this. Let's go about this the first way. Go about answering this problem. Okay. The first is to work in periods. Okay. With semi-annual compounding, that means there are 2 periods per year. Since I'm interested in how much money I have after 1 year, that's after 2 periods. Okay. And these periods are every 6 months. Period 1, period 2. So if I'm going to work in periods, I better compute a periodic discount rate. That's I, which we know is APR over K, and which in this case reduces to 2.5%. In other words, I'm going to earn 2.5%. I'm going to earn 2.5% over the first 6 months. Then I'm going to earn 2.5% over the next 6 months. Erase that. Okay. So I take my initial $100 investment, I multiply it by my periodic discount rate, and after 1 period, I've got $102.50. Then I repeat. I take that $102.50, I multiply it by my periodic discount rate to get $105 and a little over 6 cents. In other words, the future value 2 periods hence of $100 in this setting is just 100 times 1 plus I raised to the power 2. We're working in periods, so I is our discount rate, and 2 is the number of periods we're moving the money forward in time. Now let's approach the problem from the perspective of years. Now we're looking for how much money we have after 1 year. But if we're going to work in years, okay, now we need to be consistent. So after 6 months, this isn't 1 period, this is half a year. And because we're working in years, our discount rate isn't going to be the periodic interest rate I, it's going to be the EAR, the equivalent or the effective annual rate, which we know from earlier is just 1 plus the periodic rate raised to the number of compounding periods per year, so 1 plus I to the K, which in this setting comes out to 5.0625%. In other words, over this entire period, I'm going to earn 5.0625%, right, which turns out to equal $105.06, a little over 6 cents. That is, the future value 1 year, excuse me, 1 year from now of $100 is the $100 times 1 plus the EAR raised to the power 1. We're working in years, which gives me the exact same answer we got before, the $105.0625. So the lesson: if you discount cash flows using the EAR, then you better measure time in years. If you discount cash flows using the periodic interest rate, then you better measure time in periods. And the equality between the two that we just showed with our simple example is much more general and given by this straightforward proof, which I'm not going to discuss in detail, but I'll show you there if you're interested in looking at it. So just to summarize, we can work in periods, right? 1, 2, with a periodic interest rate, or we can work in years with our effective annual rate. Okay? And notice I measure everything consistently, periods versus years. Okay. So let's go back to our original example. Excuse me. We had an APR of 2.37%. We have a compounding frequency of daily, which I'm going to assume is 365 days, though you should be aware it could be 360 days or it could be 252 business days. It depends upon the convention used for that product by that institution. So these two pieces of information, the APR and K, allow me to compute the periodic rate, I, which is 0.006741%. Now that's a tiny number, but we're computing interest every single day here. Which means the effective annual rate, which equals 1 plus I to the K, or which in this case is 1 plus 0.006714% raised to 365th power, gets me to just under 2.4%. So when we round the 2.398, we get about 2.4%. All right, so let's summarize. We learned that there are two discount rates depending on what units of time we want to work with. If we want to think in terms of periods, we want to use a periodic discount rate. That's I. If we want to work in years, we want to use the EAR, the effective annual rate, which relies on cash flows measured in years. Both of these are discount rates. They'll both get us to the same goal or the same end result, but we have to be consistent in terms of how we measure time with which discount rate we use. APR, that's a quoting convention. That's a means to an end. We use APR in conjunction with the compounding frequency to get our discount rate, whether it's the EAR or the periodic interest rate or the periodic discount rate I. And we can move between the APR and I and the EAR by a couple of very simple mathematical relations that we discussed. Now, next are a bunch of great problems that I want you to dive into. And then after you're done with those, move on to the second part of interest rates, in which we're going to investigate the term structure of interest rates and talk about the yield curve. Let you know what these things mean. Thanks so much.